सर वो पीपीटी भी जरा आप भेज दीजिएगा, पीडीएफ जरा, कल एक्चुअली इन लोगों का क्विज है ना।
हाँ ठीक है,
तो उसमें से कुछ क्वेश्चंस हो सकते हैं क्विज में।
अभी स्लाइड आ रही है क्या?
हाँ स्लाइड
घूम रही है,
स्लाइड शेयर फॉर्म में तो आ गया है, लेकिन अभी स्लाइड दिख नहीं रही है,
रोटेट नहीं हो रही है,
दिख ही नहीं रहा है अभी तो। शेयर
तो
जैसा कुछ हुआ है बट विजिबल नहीं है।
क्यों नहीं?
शेयर में से करिए। कॉलेज का नेट यूज कर रहे हैं?
हाँ कॉलेज वाले में। आ रहा है स्क्रीन में?
हाँ स्क्रीन नहीं आ रहा है सर, आप शेयर करिए।
शेयर तो कर दिया ना।
नहीं आ रहा है कुछ, नेट का कुछ प्रॉब्लम है क्या वहां पर?
अब देखो आ रहा है।
वही राइट हैंड साइड टॉप पे जाके शेयर करिए।
हाँ वो किया मैंने, सबका दिया, वो तो पीडीएफ भी ऑन कर दिया है।
फिर से एक बार निकल के वापस ज्वाइन करिए। अभी आ गई, अभी आई सर अभी आ गई स्लाइड आपकी। हेलो आर्या सर।
हेलो।
आप हाँ नाउ इट्स कमिंग फाइन।
हाँ हेलो।
हाँ तो अभी जो है नाउ वी कैन स्टार्ट। तो participants in continuation if Arya sir's previous lecture, now some parts that was not covered in that session. Sir is going to cover today, and I hope so you will enjoy this session. Now, Arya sir, you can continue.
Okay. Now we will start.
Yeah.
So today we will tell one of the basic element in power quality area. Means we want to design one shunt active filter, or maybe you can say advanced version of that one in the DStatCom for renewable energy application, or maybe any other application, grid connected or maybe non-grid connected. In any case we can use this one, maybe based on the grid, or based on the isolated system, or based on the renewable, or maybe based on the any other applications. So we want to tell how we can design this device, how we can operate, what a control circuit, some basic point only. You see here, in this case, what is the basic function of this device is, generally this is the shunt connected element with grid. Maybe you can design single phase or three phase. In case of single phase system, maybe you have a two-leg converter. In that two-leg converter, maybe you can say, two-leg converter means only line ground is there, so you can make a closed path. The point is, in this case, basically problem is harmonic and reactive power. But if we are going to see three-phase system and three-phase, three-wire, maybe three-phase, four-wire system, in that case, we want to connect shunt active filter in distribution network, which is used for mitigation of current-related power quality problems. Means we want to mitigate current-based power quality problem, which is generated by the load only. And we want to maintain supply side almost fundamental active component with distortion free. And also active component means unity power factor, you can say. In this case, basic function of the device is you can say reactive power compensation, harmonic suppression, load balancing, neutral current compensation, or maybe these are four problems are there in a three-wire system and four-wire system. If you have four-wire system, fourth problem you are going to observe. So configuration, maybe you can say three-phase, three-wire, or maybe three-phase, four-wire. In three-phase, many topology you can observe in literature: three-leg, four-leg, three-leg, four-leg, maybe three single-phase, two-leg, any other also there. By three-phase, four-wire system also you can say three-phase, three-leg VSCB transformer, four-leg, three single-phase. Again, transformer based many connection also you can observe. This is the means topology of the active filter, shunt active filter. In that case, means you can take circuit. The circuit is based on the voltage source converter. You can develop required level of DC link voltage. And that based on the power flow, this one may be work as inductive or maybe capacitive. Okay. So generally, this complete network or complete DStatCom working in two mode. First one, the power factor correction mode, means we want to maintain unity power factor between supply, unity power factor between, or maybe you can say unity power factor supply end, and we want to maintain zero angle between fundamental active current and voltage. That you can say. And after making the power factor correction mode, maybe you can run the system in zero voltage regulation mode. Means we want to maintain rated voltage at PCC value. Even load is going to increase or maybe decrease or maybe any other value. Okay. Means this complete system is going to work in two more. The first one is based on the power factor correction, normally just like a active filter. After that, active filter is advanced features you can see. A second case, this one is going to work as a voltage regulation mode. So point is to see the circuit diagram. Here circuit diagram, first one is maybe three-wire system you are going to see. In that we have a three-phase source. Slide is coming now? Slides and voice. Hello?
Sir.
Yes, sir. Yes.
Now you can see supply source is there, three-phase, three-wire. And then after that, you are going to see three-phase, three-wire load. Load may be non-linear, linear, depend upon the consumers. Again, point is there. We have a supply source with neutral wire, maybe neutral grounded, not grounded, depend upon the conditions. After that, we have source impedance. See that due to source impedance, what type of wave we are going to observe, or maybe how the voltage is going to distort at terminal of the load. Okay. See, suppose we don't have one case we don't have any source impedance. So what type of phenomena are we going to observe? Our supply source is towards maybe sinusoidal, can maybe distorted. Okay, that one is going to appear across the terminal. Okay, or maybe supply current is going to distort due to load. One thing. Second thing, main point, how source impedance is going to play major role here. The point is, suppose we have R and LS. R is there, okay, R is the resistive element, only some drop you are going to observe, but inductor is there. See the inductor, and now also you can see the nature of current. Nature of current is not sinusoidal. We are not saying this is the pure sine, maybe pure non-sinusoidal, maybe you can say some mixed type of nature are there. Or nature of inductor is, what is nature of inductor here? This one is going to make derivative of the current. Now, so if a current is non-sinusoidal, you are going to make derivative. Due to that one, you are going to observe change in nature of supply current, or maybe you can say load current. Here, if you don't have any compensator, na, see the nature of supply current and load current both are same here. See the due to derivative of the inductor. Inductor means due to source impedance we have inductor. And in that, what is the voltage? VL equal to EL di by dt. So due to this IL, value of voltage cross inductor going to change now. Because your current is non-sinusoidal. Or derivative of that one also going to change. Our continuous many derivatives are going to observe. Due to one shape of that continuous is going to change. Finally, this one is also going to distort your terminal voltage VT near to load. It means if value of inductor is going to increase means that you can say VL L di by dt, II non-sinusoidal, then you are going to observe change in VL, voltage cross inductor, and that one also going to affect your VT. Okay, so means due to source inductance, value of source inductance is going to increase. Due to that one, we are going to observe change in nature of IL, maybe increase or decrease, but value of IL is, if value of LS is high, then that also going to affect the value of VT. Point, okay? So due to source impedance, your terminal voltage is going to distort due to change of the nature of IL. Okay. So now you can see, after that you can see, so after that you have here non-linear load. Non-linear load is going to do the non-sinusoidal current, that we want to compensate with the help of voltage source converter. Here we have voltage source converter with DC link, then we have a LF, then also we have a ripple filter. So ripple filter is going to, what is the role of ripple filter? That one is going to provide a low impedance path after certain value, for certain switching noise you can say. Here basically we want to maintain DC link voltage how much? More than peak value of line to line voltage. This is our requirement. If we are able to maintain DC voltage more than peak to peak line voltage, then this converter is going to work as a compensator. Means by some method we need to maintain DC bus voltage higher than peak value of line voltage. After that you can see that output of the converter phase A, phase B, phase C. At that one we have connected to phase A, phase B, phase C line. In that with the source with the LF. So LF is responsible for making the power flow between line to converter and converter to line. LF is responsible for making the power flow between line to converter and converter to line. If converter voltage higher than line voltage, then power is going to flow from converter to line. If line voltage higher than converter voltage, power is going to flow from lower side. Okay. And also whatever source inductance we have used, the source inductance is going to provide good quality of, means that one is going to reduce the sharpness of noise in compensating current. Okay, mean dual function you are going to observe. So this is the over hardware. Also you can see the how that rectifier with RL load. So we have a rectifier, and output side maybe you can connect RL load, maybe RC load. So RL means you are going to maintain constant current with the help of inductor. One thing. Second thing, maybe you can maintain constant voltage with the help of capacitor. If we have RL load, means rectifier with R and L. It means in this case, in case of uncontrolled rectifier, maximum distortion you are going to have not more than 30.25 or 35 like that. Okay, and based on the source impedance, because here source impedance also going to play the role, and that one is going to observe some value of harmonics. So maybe you are going to observe distortion maybe 27%, 28%, 29%, depend upon the source impedance. Okay, That is the basically depends on the source impedance only. If we have RC load, second case, if we have RC load, in that case, what is the point? With a rectifier, you can get R and C parallel. Okay. With the help of C, you are going to maintain the constant voltage. Okay. And to maintain repeat-free constant DC voltage, we need some calculation. If you are going to 0.1%, 2%, maybe 0.5%, based on that one, you can make the calculation of the C. Based on that C, if C is so high, that one is going to conduct only upper level of the current only, not going to means your voltage not going to become zero immediate, or not going to increase very high, very fast, you can say. So your conduction only going to up to upper level only, means just no dust means peak near to peak only. So you can say in that case, this converter going to draw a somewhat peaky current. In that case, we cannot say our system had this much distortion, maybe 20%, maybe 50%, maybe 200%, maybe 70%. That value is not fixed. That depends upon the how much capacitor you have put at the DC side of the rectifier. Means here we have two types of, one is a constant current load, second a constant voltage load. That you can see from books. Many books they have given. Also you can see the how source impedance is going to affect. That is also main point here. After that you can see we need one control logic. That based on the control logic you can decide the gate pulses. Means gate pulses also we need to generate with the help of some controller or maybe some method. So we need to generate gate pulses. Okay, so that gate pulse means you can design. Here we have used, maybe you can use direct current control, maybe you can use indirect current control. In case of direct current control, we have to generate the directly compensating current. This is one method. Second method, maybe you can generate indirectly, means generate the reference current compared to source current. After comparing whatever is coming, that error means our reference current is sinusoidal. We are telling we are going to generate reference as sinusoidal. At that one, you are going to compare with your load current. Maybe source current you can say here. Source current. Source is non-sinusoidal, or that is sinusoidal. So between that one, we have some error. At that error, if continuously going to improve, if our converter going to on. Okay, means after converter switch on, our source current is going to become sinusoidal. A continuous this have iterations. So finally, you are going to compare reference current from sinusoidal near to sinusoidal source current. Between that, you have some error. Based on that error, if both two sine wave we are going to compare, if we have a comparison of two sine wave, then in that case, error also sinusoidal, but thick sinusoidal. In that, you have a distortion or maybe that noise component. That with the help of that one, you can generate the gate signal. The C point means here we are going to use two type of method. One is the direct control, second the indirect control. Similar to second case, you can see. Second case we have 4-leg converter. 4-leg converter means we have a 4-wire system. 4-wire system means in that case we have 4 power laws. One is the reactive power, second the harmonic, third is unbalancing, fourth is the neutral current. Okay. The point in neutral current means with the help of 4 legs, you can compensate the neutral wire current. In this case, we are going to use 3 single phase load. Assume that we have 3 single phase rectifier. So their phase you can connect to line, and second wire you can make common, connect to neutral wire. Okay. At that common point, you can connect to 4 leg inverter output. So that your load neutral current and compensate neutral current both are going to compensate each other. Compensating current ICA means 4-wire current is equal to opposite of the load neutral current. If rating is sufficient, if some less rating is there, up to sufficient value that one is going to compensate. Okay. So finally we have source side somewhat very less value of neutral current, maybe 0 almost. Some noise is there. This is the active compensation of the neutral wire current. Otherwise, you can take transformer connections also. Transformer maybe you can take star delta, zigzag connection, T connection, or maybe Scott connection, many connections you can take. That is passive composition only, so the passive composition only, so that neuter can easily we can compensate with the help of passive element, because that will not going to change so much. If you want to make active composition, you want to save the space, you want to make somewhat complex system, you can take two more IGBT and modify the control circuit. Here you can see other three legs. Other three legs they are going to compensate reactive power, harmonic, unbalancing only. These three problem only. And you can maintain DC bus voltage how much? More than peak value of line to line voltage. This is our requirement. This is condition only. And whatever the RC filter we have, that RC filter is going to provide low impedance path. Suppose you can the R and C. The impedance you can see R is fixed. X equal to how much? 2 pi FC na. The F, if F is going to increase means your X is going to decrease. That near to fundamental when frequency of component is somewhat lower. In that place, this one is going to provide impedance. Other cases.
सर स्लाइड चली गई आपकी.
Hello. So now you can see. In this case, first point is see the component. So whatever R and C is there. So R is fixed. We don't have any frequency component. But in case of XC, 1/2 FC you can take. If F is going to increase means your value of XC is going to decrease. Means we are telling this circuit is going to provide low impedance, which is more effective more effective at higher value of frequency. For higher frequency component, this circuit is more effective, you can say. Means this one is going to provide somewhat lower value of impedance for high frequency noise. Simply you can say like this. Okay. Any question? Hello? 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 Hello, anyone? Anyone? Voice is coming or not coming?
Yes, sir, it is coming, but slide is not coming.
Okay, that will come now. Now slide you always to see slides?
Yes, sir. Yes, sir.
Okay. Now point is there. Means see here we have taken 3 single phase load. That is also there. Next point is, so in that case, whatever this state we are going to say, that in that case many control logic we have observed. In the lecture you can see so many cluster control, maybe adaptive controller, maybe you can see that neural network, fuzzy logic, all the people they have used. So based on that one, you can design that point. Now point is how we can set the value of DC link voltage. So see the value of formula is there. So you can see first whatever line to line voltage. The line, if line to line voltage 415 now, then you can put 2√2 415 divided by √3. Here may be the modulation index. Okay. So based on the value of, based on this formula, you can set the DC link. Or maybe you can say from this point our converter is going to work as a capacitor. For sufficient, you can take nearby round figure value, you can take, not a problem. Okay. Point okay. Basically, simply also we can say we are going to take somewhat peak higher than peak value of line to line voltage. That is also one guideline. And now how much DC link capacitor we can take? So you can take the one. Hello. You can take 1/2. We can take 1/2 CV square equal to 3 VIT. Means both sides we are going to observe energy balance. This is one guideline. Second guideline is for each 2 kVAR. Suppose our converter is rated for 2 kVAR reactive power. For each 2 kVAR, we can put how much? 2000 microfarad. This is again one more guideline. For each 2 kVAR system, we can put 2000 microfarad. So for you can say, no, not 2, for 5 kVAR. For each 5 kVAR, you can put 2000 microfarad. So for 25 kVAR, you can put 10,000. That is also one guideline. Okay. And after that, we can see here we have designed the value of that capacitor. Then capacitor we have got 10,000. This calculation also you can see paper, many paper we have given that you can see the calculation there. Now you can see based on this formula also CDC equal to ID divided by 2 omega VD CRP. Means based on this formula also we can design the value of DC link capacitor. You can see what is our converter rating? 25 kVA. Capacity voltage how much? 700. So you can take 35 ampere current. Now we are going to tell in DC link voltage we are going to maintain almost ripple free. We are telling maybe you can maintain less than 1% ripple on DC bus voltage. Less than 1% means near to 5 volt, 6 volt. That depends on your choice only. So you can put that value. So in that case, you can see ID equal to how much? 35 into 35.71 divided by 2 pi omega into 5. So that based on that one also we can calculate. So these are two formula are there. You can use any one, or maybe simply guideline also we can use. How we can select interface inductor? Again that formula is there. √3 EMA VDC divided by 12 alpha frequency and ripple current on the compensating current. Compensating current means output of the voltage source converter. That converter is going to carry a capacitor. You can see √3 EMA is one only you can take. DC link capacitor you can take, DC link voltage you can take 700. 12 alpha you can take some holody factor, some value you can take more than 1, 1.2, 1.3, 1.5 depend upon your value. Frequency you can take 10 kilohertz. Ripple on the compensating current means percentage ripple on the whatever converter is going to provide the current. At that one is going to compensate your reactive power harmonics. In that case we take 25%, about 10 to 25 any value you can take. So here we are going to take 2.5 millihenry we have calculated. So rough guideline is if your current, your maybe load current is near to 7 to 8 ampere, na, you can take 2.5 or maybe 3 millihenry. Whatever experimental data is there. For 110 volt, 7 ampere, 8 ampere load current, you can take 2.5 near to 3, not more than that. Suppose your voltage is going to increase in view of 110 volt, that voltage is going to become 415 volt. So based on that one, this value also going to increase. So we have run the system 415 volt with 4 millihenry, 700 DC link voltage. Based on that data, we have run the full voltage dictate count. Also, you can see switching frequency, how we can select the value RNC. So generally, switching frequency people are going to take between 5 to 10 kilohertz. Any value you can take. Here we have taken 10 kilohertz. See the RC filter calculation, just you can read once. Selected value of RC filter element is 5 ohm and 5 microfarad. This series circuit of RC filter is connected in parallel with the each phase of PCC voltage to ground. Clear now? But each phase you can connect 5 ohm, 5 microfarad. This data is for 415 volt. Mean full line to line, full line voltage. If 110 volt or maybe 230 volt, your capacitor is going to increase. Maybe 10, 15, 7, 8, depend upon the how you are going to tune. That tuning also going to take so much time here. Okay. Then one more guideline is there. R, F, CF. We can time constant of that one. You can take very less than TS divided by 10. That is also guideline. Okay. This filter provides low impedance path to separate the switching noise and high frequency path for fundamental frequency. At half of the switching frequency, 5 kHz, filter provides low impedance path, maybe 8.09, to separate the switching noise, and high impedance path at fundamental frequency maybe 636.63. So see the calculation. R plus XC. So XC you can take, R you can put some value. R is independent of the frequency. XC is dependent upon the frequency. That point you can see. Clear? Any question here, design? Or maybe you can read some paper also. We have given the design, how we can design the component. This is a very mature field. You can say here we have many calculations we have done based on this. How we can say the IGBT? So we can see the DC link voltage. In that 10% star you can add. But point is there, in market maybe our DC link voltage 700 plus 70 means 770 DC link IGBT we will not get. If we are going to design 770 volt IGBT, that is special design only, more costly. So maybe you can take double or maybe higher rating also you can take. For the whatever regular item are there, that you can take. What about current rating of that switch? You can take 1.25 peak value of the current plus ripple on the current. You can take 1.25 in bracket ISP plus ICR, where ISP is the peak value of the voltage source converter current. ICR is the ripple current on the ripple component on that current, you can see. Clear? So in that case also we can calculate, but we are going to see some higher side only. As per market survey or available component on the market. Based on that one we want to do work. Clear? Now you can see here we have taken 1200 volt 200 ampere IGBT. Now in case of fourth leg, we have fourth leg converter also. In that case you are going to see inductor value going to increase. Whatever inductance you have in 3 leg, somewhat high value you can put, because in that case we don't have any counter here. Means suppose you have 2.5 milli, you can put 4 milli. For that one also we have formula 3 MA VDC divided by 3 root 3 alpha FS ICR PP. Means alpha overlapping factor 3 root 3 the value only. FS is the switching frequency. ICR PP is the ripple current on the compensating current. Ripple component on the compensating current you can see. Okay. This is our guideline only. But based on that one you can modify here and there some value. That's not required. Which is based on that one we will get some approximate value. This value we will put. Based on that we will get the answer. That is the point. So now you can see, now we have seen the power circuit. Now we want to see the control circuit. In literature, many controller we have done. We have design also. So that you can see. Based here we are going to say based on the somewhat adaptive control. Means how we can find out the value of their weight. I mean that means average value. Or maybe component, maybe active component. Their weight value based on the iteration based method. That value going to change based on the learning rate. Whatever learning rate you can put, maybe fixed, maybe variable, maybe depend upon the estimation also. The based on learning rate, that value of maybe WP or maybe WQ is going to change. That is main point. Means active weight and reactive weight we are going to change or we are going to modify. You can see here we will tell by very basic method only. That is based on the this diagram we can see. This is the based on the one fixed learning based method. Okay. We are going to use one fixed learning based method. In that case, learning rate we have put fixed. So just one by one, I explain one part. See the upper part. So DC link voltage we are going to sense by sensor. You can put low pass filter. You can in the output of the DC link you have a second order harmonics. Okay, and also you can put one VDC star. We can put one VDC star. And also we can sense. So whatever voltage you want to put, that voltage you can set. Here we want to put 700 volt. 700 volt DC. First we want to develop. That is our requirement. That we want to decide. We have to we have to put peak value of line to line voltage. So we have put 700. Now after rectification, whatever three phase rectifier is there, how much voltage that the rectifier will give? 3 Vm by pi you are going to observe. After means we are going to get DC bus voltage from rectifier only. After the rectification from rectifier, you are going to get how much? 3 Vm by pi. That voltage you are going to observe. Both you can compare. After comparing, we have error. That error you can regulate with the help of PI controller. How we can regulate? Put the KP, KI, some value you can put. After that, your sense voltage is going to touch the reference voltage with steady state value. Are going to maintain zero error between sense and reference. At that position, output of PI controller is minimum constant DC. That you can take. Second case. Now we want to find out active component of the load current. Upper loop, lower loop is the reactive component of the load current. So for that we have to sense ILA in phase template that you can find from voltage. Load can be phase B template, phase C load current, and phase C template. With 3-phase template or 3-phase load current. How we can calculate template? This formula is there. First you can find a terminal voltage amplitude. 2 3-phase voltage that is square divided by 3. That is Vt. Then in phase template equal to their phase voltage divided by Vt. For phase A, for phase B, their phase B voltage divided by Vt. Vt the amplitude of the PCC voltage. US PC is the phase C voltage divided by Vt. Okay. Also we have to find out the quadrature component of these. So for quadrature component, what we will do? We have to shift. See the equation number 13, 14, 15. So based on the in-phase component, you can find out the quadrature component. That formula is fixed. After he can also shift by 90 degree. But in that case, if frequency is going to change, then that's it. That their 90 is not going to follow that one. So we want to shift based on the formulation only. So that frequency effect we are going to include here. Because frequency 49.95, 97, 98, 50.01, that change is going to become. Then your control is going to affect. Clear? Now you can see. Now next point is we have changed the load current. Template also we have taken. So see the equation number 8. What we have done? We are going to take new sample of phase A equal to old sample of phase A K minus 1 plus tau. In bracket you can write IL minus WLPA, the old sample only, plus into template. So what is the nature of IL? IL is a non-sinusoidal. Nature of ILP is the DC only. Nature of the UPA is that is the new template. So if DC value multiplied with template is the, suppose DC is 20 into template is 1. So 20 into 1 means you are going to get sinusoidal 20 ampere or 20 amplitude you can say. So that value you can subtract from load current. Means non-sinusoidal current minus sinusoidal current you are going to subtract. Non-sinusoidal load current minus sinusoidal estimated value. We want to subtract. After that you are going to get the error. That nature of that error is almost AC only. Sine therefore square minus sine, in rough case we can say square minus sine is, you are going to see the wave. In that you have a AC component, not DC only. Again AC component you are going to multiply by AC component. What we will get? If AC into AC means we will get some DC value plus some offsetting component. So based on that theory, they have developed the equation number 8. Again, we are not going to take whole that component. We are going to take some percentage of that value. Maybe take 70%, 80%, 50%, depend upon the your load current. Load current of 5 ampere. You get 1%, 2%, or maybe 10% not useful. You get 70, 80% you can take. Load current 50 ampere. Take 3%, 4%, or maybe 40%, 30, 40 or 50% you can take. Okay, so that linearity is going to change. In that way, we have final value of active component of the active weight of the load A current, WLPA. So same formula we have written here. This formula you can see. Upper box, first one. Just you can check once. Upper box, first one. After that value multiply. After that, you can see phase B also we have find out. Phase C also we have find out. All three you can add. After adding, put low pass filter, because in that you have a offsetting component. Then you are going to observe WLPS after adding. Then that value is add with output of PI controller, WCP. Okay. After adding total component WTP. So WTP divided by 3. That is going to become WSPA. This term we have given only. So finally, we want to find out the average value of DC bus PI output plus total value of active component. Or maybe before low pass filter also we can divide. Not a problem. But if we are going to divide after means adding, then effect on the DC bus is going to reduce. So finally, we have got the value of this. What we have got WSPA. At WSPA, this is the average value only. Multiply with in phase template. You are going to see. You are going to observe active component of the phase A current. Active component of phase A reference current. Clear? Similar way you can find out the active component of phase B current. I star SPB. The WSPA. This is average value into USPB. Okay. ISC star ISPC equal to third phase active current equal to WSPA into USPC. Clear? How we will get the value of active component? This is clear? Any problem here? Now second case you can see. Upper box we have used the in phase template. We have found out the active component. Now we want to find out the value of WLQA. WLQ small a. Reactive component of phase A load current. Their weighted value. So present sample equal to old sample plus tau load current minus your reference current. Reference current, how we can find out? Reactive component, their weight into quadrature template. Clear? Means non-sinusoidal current minus reference current, you will get the some error. And nature of that is almost sinusoidal. Okay. You can find out what terminal voltage. represented a VT charge. What is the VT? Basic
Sir, some disturbance in your voice, sir. Maybe due to internet. Sir, your voice is not audible. हेलो सर, डिस्टरबेंस है अभी भी. जतिन सर, Jatin sir, is it from our due to our end or sir's? Okay, okay.
Hello.
Yes, sir.
And we want to find out WMD. Yes. Hello. Void कहाँ है? Okay.
There may be some issue related internet. Please wait.
Now voice is coming.
Yes, sir. It's now coming.
Now you can see this is a total control logic for three-phase, three-leg system. We have generated ISA star, ISB star, ISA star. Compare with their actual value of source current. Then then after that, means finally what we are going to do, ISA star minus ISA. This we have to do. In that case, error will come. That error you can compare with triangular wave, you can say with certain value of switching frequency 10 kHz, 5 kHz. Then you have gate signal. At that gate signal you can apply first leg upper IGBT. First leg upper IGBT. For lower leg, same gate pass you can pass for NOT logic. Then you can lower IGBT. Similar you can do for phase B, phase C. That whatever gate pass you are going to get from directly, you can connect to. You can give to upper IGBT, by NOT due to lower IGBT. Phase C also, directly whatever gate pass you are going to get, give to upper IGBT. From NOT, whatever signal you are going to get, that is also gate pass only, due to lower IGBT. Okay, this is the point. Simply we want to design sine PWM. Clear? This is the one of the elemental layer. This one we can apply anywhere. Wind, solar, hydro, or maybe vehicle, anywhere we can apply. After that, you can see here. This is our controller. Now you can see how we can see the result. Result you can see in PFC mode. We have plotted supply voltage, supply current, neutral wire current, phase A, phase B, phase C load current, transformer load neutral current, three-phase compensating current, terminal voltage, and DC link voltage. Okay. So see, after compensation, this is the result of four leg converter. How we can design switching for four leg? We want to maintain zero neutral wire current. Zero you can put, and that zero from sense value of neutral wire current. You have a one signal. That signal compare with your carrier signal of whatever gate pass is coming. That gate pass you can give fourth leg lower IGBT. Here we have put reference negative. Our sense positive. But in case of PWM, in case of other three legs, reference we are putting positive, other one we are putting negative. So due to this one, whatever that pass is coming, that pass you can give to lower IGBT. After passing NOT logic, you can give to upper IGBT. Clear? Here opposite work is there because we have put reference as a negative. So see here, after compensation, neutral current is how much? Zero only. Before compensation, see the neutral current. Frequency of neutral current how much? This is third harmonic only. And due to abnormal condition, that value going to increase up to maybe √3 into IL. But 57% eastern neutral current you are going to observe. That is problem. Okay. So due to this nature, due to this point, due to problem of this neutral wire current, we have to compensate. That is point. See the nature of compensating current. So that compensating current, they are going to change their nature as per condition of load. As per condition of load, they are going to change their nature. See, at 0.9, load current is 0. If 0, we are going to admit sine wave, then you have a sine wave, na? If this point you can see. So at phase B, some other wave is there. So see the nature of a compensating current going to change. Phase C, some other wave is there. Then see the nature of compensating current. Means nature of compensating current dynamically will change. Provide the compensation, maintaining the your you can say supply current sinusoidal, the sine wave only. Also balance also with less magnitude, you can say. Sinusoidal balance with less amplitude. In PFC mode, see the problem. Our terminal voltage here rated value 339.33 amplitude, means 239 point some value into √2 you can do, then you will get the 339 point some value. After that, after putting this much, maybe 50 ampere current, your voltage going to dip up to maybe 335, nearby that 335, 37. This is due to loading of the system, or maybe due to voltage source voltage drop. Okay, so this one we want to compensate in this voltage we want to compensate with the help of VT loop. See the second figure. See the second figure. In that, your VT is maintained almost 340 volt. VT is maintained almost 340 volt. After compensation, you can see. Okay. So we want to maintain, or we want to increase this value up to 340. For that one, we have used VT loop. VT loop, what time VT loop we are going to run? First, you can run your system in PFC mode. After completing PFC mode, after means achieving the PFC mode, then you can run VT mode. Okay. So first you can tune DC link voltage, DC link PI. Then you can tune, after getting the proper DC link, proper compensation, proper PFC mode, then you can tune the AC bus PI. Clear? And other similar response you are going to get. But problem is there in ZVT mode. Always we are going to observe nature of supply current leading in the comparison of supply voltage. This is problem. So leading power factor you are going to observe in this case. In this case, we are going to observe somewhat leading power factor. In ZVR mode, we are going to observe somewhat leading power factor. That is not useful for us. So people are going to use only ZVR mode, PFC mode only for grid connected power quality improvement. Suppose they want in wind or maybe hydro power plant for compensation of power quality problem, they will use VT also. That is small system, in that angle is somewhat very less only. Okay. Clear? See the waveform, how we can analyze the waveform. Supply voltage, supply current, then load supply neutral, maybe almost 0, then some noise is there, high frequency noise is there. If we are going to put one more inductor, then that is going to remove in source side. After making connection between compensating neutral and load neutral, one wire will come. In that wire you can put a small inductor 2 millihenry. Then totally this will remove. Then you have a load neutral. As load can phase A, load can phase B, load can phase C, or 3-phase current. Clear? Then you are going to observe load neutral current. Load neutral current near to You can see maybe near to load current only. Then compensating current phase A, phase B, phase C, then VT, then DC link. This is a DC link near to 700 we have maintained. And doing dynamics, you have some change. So see what type of change we are going to observe. Doing dynamic condition 0.9. 0.9. See the first Nikki that step, second step, third step, then fourth. Means why we are going to get this type of waveform? Our PI is going to react. Just after switch open, voltage increase, again increase. Then PI going to generate the action, and that value going to decrease continuous. If PI is not going to react, PI not going to work now, this value continuously going to increase and become more than 700, 710, 20, 30, 40, 50. Maybe after some time your DC is going to burn also. Okay. So in that way you can see if you have this type of proper Nikki that increment decrement. If we don't have an increment means your PI not going to affect. That is also wrong only. Means we should have both phenomena, increment and decrement. That point is there. Okay. Maybe we don't have anything now. Maybe we have put so high capacitor. Means in that way, no, nothing is going to affect like that. After you can see at steady state level of distortion. In single phase system, suppose single phase diode will rectify with RL load. Single phase diode will rectify with RL load. Okay. In that case, how much distortion we are going to observe? Maximum 48%. See the Bhimra, see maybe any other book. All the books they have your derivation also. What is the level of distortion? How we can analyze the input of the rectifier, current with the alpha Fourier series. Or maybe you can find out from that MATLAB, maybe there, so you can connect, you can find out. So here we are going to observe 48.66. Means ideal is 48, but due to source impedance, this had decreased up to 3%. That is the point. Okay. Ideal is 48, but due to source impedance, this decrement we have done. Now point C. This is our load current. See the supply current. Supply current is after compensation in supply side, you are going to observe 3.15 distortion. Okay. What about current? After compensation, you are going to observe that fundamental current less than load current. Here we are going to observe somewhat very less difference only because only distortion we have observed only. So your load current 48.86 peak value, after compensation 44.01. But if we have a inductive element also or other element also, then this is going to become large change you are going to observe. Here current level is also 40 ampere only. If you 100, 200 ampere, 300 ampere, this will change. This change you are going to observe more. What about value of supply current, supply voltage? So supply voltage you are going to observe how much? Phase voltage, their peak value, distortion is 2.29. Clear? This is the whole about the PFC mode. Now PFC mode you can see we need 339.9 and 339.25. But here you are going to observe due to loading 335.4. This one we want to compensate up to rated value. We have compensated up to 338.7 with the value of 2.23% distortion. After compensation, see the value of supply current 44.79, load current 45.29. Clear? Clear na? You see what is a ZVR mode? ZVR mode means we have compensated the voltage. PFC mode means whatever PCC voltage comes, you can take that one. After that, you can see the comparison. One comparison we have, not comparison, one data we have made. Supply PFC mode, PCC voltage, supply current, load current, PCC voltage. In case of ZVR mode, supply current, load current. In percentage distortion, you can see that. Okay. This is the one of the basic controller with fixed learning. Okay. After that, also we can change same formula. We can change the learning rate. Or the learning rate you can find out from estimated value. Learning rate we can find out from estimated value. Or find out from estimated sense value of current. The load current you can take, and based on the formula you can see our this is the formula for this is a formula. How we can calculate tau PA for phase A? So 1 divided by 1 plus beta 1 e to power minus beta PA Kp. So beta PA how we can find out? This formula they have given. That paper also available online only. So lower upper means old value plus theta error lambda tau PA 1 minus tau PA error and some K constant. Error, how we can find out error? Error is the phase A weight minus total weight. Phase A weight minus average weight. We have three phase voltage, three phase weight. Phase A weight, phase B weight, phase C weight. Their average value also we can find out. So from phase A, you can subtract average value. KKR is, again their square and norms. Error is, you can find out active component minus load current into phi A, into template you can see. This is the DC value minus load current into template. Phi K means template only. So template sine wave, load current is sine wave. Towards the sinusoidal, now sinusoidal. So total become sine into sine means total become DC plus oscillating component. So DC minus DC, then oscillating component. That oscillating component we can take error. Clear? So in that way, we have modified the value of tau. Tau modification we have done with the help of whatever sense signal we have taken, a current, voltage, or some other component, maybe some constant. Based on that one, we have modified that one. So you can see how this one is going to react during that dynamic condition. So see tau PA. If load is somewhat unbalanced, so tau is going to become so dense. But if load is balanced with three phase, then you can see tau is going to become somewhat discrete time. Okay. See the value of tau PA here. See the value of WLPA. How active component is going to change. After that, you can say means filtering. See the values are more constant, the average value. So total WLP means you can see with adding the PI controller output. See the change in that active component. Mu QA, you can see. WLQA, you can see. Total value you can see. Then average value. Then total value you can see after PI adding. So see the reference current. This is our reference current you can see here. IS1 reference. IS is the actual. So both they are going to follow each other. See how, when dynamics you are going to observe now, when you are going to see change in current. So this also will change, but it's mostly this one is going to change. See the nature. Means suppose we want to have some controller now, we need to take control signal parameter. Our objective is we want to find out the reference signal. Or the reference signal we want to compare from actual source current. That we want to see. If they are going to take each other or they are going to follow each other, then useful. Otherwise, system is not going to run. Maybe your gate pass is not going to become proper. Some other problem will create. After that, we want to see the performance of your complete power circuit. One is the response of performance of the control circuit. This one is there. This is there. By control circuit means by control our objective to estimate the value of supply current, supply reference current. But by using means you can say by performance of the district come in grid connected system. Means we want to see the performance of the system in connected system, you can say. So supply voltage you can see, supply current you can see, compensating current you can see, all three phases. Converter means converter, supply voltage, supply current, converter, then load current you can see, load current phase A, phase B, phase C, then DC link voltage. Clear? Clear now? So means also we need to plot this waveform properly so that we easily we can understand. Also we can see how much in the at 0.7 we have a change. We have put the dynamics 0.7 no? Near to 0.7. Then see how this one is going to catch up to near to 50 or near to rated value. Clear now? How this one is going to catch? How this one is going to increase? Clear? Same thing, ZVR mode also you can see. In ZVR mode, nature of waveform look like similar only, but we have some difference in voltage and current angle. In case of this one, current is going to lead compared to voltage. But in case of PFC, current and voltage both are in same phase. If we are going to see current and voltage from same phase only. Okay. See the VT, mean point is there. We want to compensate terminal voltage with the help of current, you can see. Simply you can see like this. We want to compensate terminal voltage with the help of extra injecting current. Clear? See the DC link voltage, maintain almost 700 volt. Any question here? After you can see make one table PFC mode, ZVR mode, you can make one table. Now also you can see the means if we have tested also this one. So supply voltage, their harmonics, load current, their harmonic 25%. This is supply current harmonic 4.8. Mean 25 to 4.8 we have maintained. Then you can see the voltage that also we have to maintain less than 4% only, less than 5% only, according to IEEE 519. Then we see the nature of compensating current. Supply power factor you can see near to DPF one only. From capacitor you are going to this capacitor is going to provide the value of reactive power leading. You can see that one. Dynamics also you can see by load change. See the supply current is going to change. DC link voltage also we can observe. Supply current, compensating current, load current you can see there. Supply voltage, supply current, compensating current, and load current. That depends on your choice how you are going to plot. Here point is there. Just we have discussed two methods. One is based on the fixed learning. Second one is based on the variable learning. In that case, we have seen their response, how that one going to react. Here test system we have developed for 110 volt. Also we have the high voltage, but 110. At present our system is running 110 volt only. Means last 1 week before also we have taken result 110 volt. Right? And that is developed based on the sensor, then you can say converter plus a RC filter, then computer one processor. Then you can see here that sensor LM sensor we have taken, rectifier as a load we have used. Future maybe you can use more controllers, maybe you can develop applications, maybe you can use isolated, non-isolated mode, you can use hydro, wind, solar, transportation. Transportation means at DC link you can put chargers. DC bus you can put charger. Other in that time this system is going to take current from supply to us charger side. Me at DC inside you can develop the DC converter, then charger, then many input, many DC converter you can develop multi input, single input, multi output converter, or maybe high gain converter. Those you can develop that side. Clear? Any question? If I can tell. Hello? Any question?
Participant, is there any question you can write down in the chat box?
This is the means whatever we have discussed. That one type of many that voltage source converter base this state we have discussed. Now you have many application of this one. Transportation vehicle, wind, solar, hydro, in that power quality improvement, grid connected system, maybe hybrid system. Hybrid system means solar and wind, maybe solar and hydro, or maybe wind and hydro, or maybe grid connected plus hydro or solar, whatever thing you can connect. Vehicle also mean we can develop the one charging station in that just like a petrol pump, na? That power will come, one side power will come, second side power is going to transport. In that way means many possibility are there. Just we have used one that voltage source converter in that case. Also you can use whatever area we are going to work. We have also going to work in series filter, series active filter, hybrid filter, UPQC also we have developed here. And wind-based solar wind-based system, or maybe you can say ACIG, or maybe single phase, three phase, PMSG. Those also we have developed. This is the towards power quality side. Second side is also we have working in induction motor control, that reluctance motor control. Motor drive side also we have work. If someone to work, or someone to come, you can come now. Here also we are going to provide scholarship by a charity, or maybe part-time or full-time, depend upon their condition, or maybe their point. For full-time, we need a scorecard. For any scholarship, we need a scorecard. This is the condition. For part-time, we need the NOC, this and that. If anyone want to come for PhD program, maybe that they can come. Okay, any question? Just hello. Hello.
Hello. Hello. Am I audible? Hello, am I audible?
Are you?
Sir. Any question, participants? Now we are taking few questions from the participants. Hello, participants, am I audible to all of you? Actually, there is no question in the chat box, sir. And I hope so. Things are very much clear from your session. And overall 2 sessions that you have conducted was wonderful and fantastic. And I hope so all the participants have enjoyed the session. So with this brief note, now I hope so. Any question? Just a minute. No, sir, no question. And we are very much thankful to you, sir, for joining us, delivering a wonderful session. Thank you very much, sir.
Thank you.
Okay, sir. Now the second session we will start once our overseas expert from Czech Republic, Professor Stephen, will be available. Just I am dropping one message to him. Professor Stephen is not available na, in the list. Okay. In between, I would like to invite some of our friends who have participated in this program, and they are very nice researcher also. They are doing a good job in their field, and uh, Professor Yogendra Arya sir is one of them, and he is a professor in the JC Bose University. Yogendra Arya sir, are you listening me? Hello? Just you see in the list whether Professor Ojana has joined us or not. PK sir?
Yes, yes. I'm checking.
Yeah, yesterday we were discussing with the participants also about their research findings and all. Yesterday, one of the participant who called me to, that means time was not enough to go to him. Professor Pathak, are you here? Professor Pathak, Dikshit Pathak. Yeah, if you have any query till this session, you can discuss with us. Even you can ask if you have any doubt about the programs and all those quizzes and timings and all. If any doubt you have, you can discuss with us. We are here to cooperate you in each and every aspect of this program. So we have planned your quiz on the Google form. Jatin sir.
सर अभी नहीं आया है गिरी सर.
हाँ 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 कोई बात नहीं. Jatin sir, just you give idea about the quiz. That means one response, one candidate, one response. Okay. And yeah. That means you are putting the Google link, that quiz link in the WhatsApp group at 6:30 or 6:45. Okay, that will start at that time. Okay, and what is the ending time? Okay, that means 7:45. They can submit their response up to 7:45. Yeah, fine. And one important information is, please use your name as that means exactly similar with your registered name, so that there should not be any problem in identification. Suppose someone is writing, suppose I am taking here the name of suppose Arnav Roy. Arnav Roy, if it is the registered name, then you put your name in the, that means first it is asked to put your name and then I think so email ID. है ना जतिन sir? Name. Yeah, perfect, perfect. And there are 30 questions. We can disclose the number of questions so that they can prepare accordingly. 30 questions, 60 minutes. I think so. Am I okay, Professor Jatin? 30 questions, 60 minutes. That means each question 2 minutes, right? Yeah. And a total passing mark is 70% out of the that means total. Suppose 30 questions, 30 marks. One question, 1 mark. Perfect. One question, 1 mark. Total marks, maximum marks may be will be exactly 30. And out of 30, all the participants who wants certificate of this program have to score 21 minimum. More than 21 marks you have to score. We have shared the YouTube link of all the sessions, and please go through it. Whatever the PPTs are available, we have already shared it. So there is no dearth of information from our side. Only request is you go through all these informations and don't bother about so much. That means don't bother so much about this quiz. Quiz is very simple. Just you keep your head cool. I hope so you will be able to attempt all the questions. There is nothing tough in the quiz, that I can assure you, right? We want to, that means we are not here to just, that means we are not here to torture anything, torture anyone. We are just here to cooperate everyone so that everyone can score maximum and get the certificate from this program. Now, again, we have to see whether expert has joined or not. Yes, our expert has joined. Now I am making him presenter. And Professor Deepankar Dev has also, he was supposed to join. Let me see whether he has joined or not. Hello, Professor Stephen.
Hi, can you hear me?
Hi, hi, hi. How are you? Fine.
Yeah, fine. I'm ready.
Yeah. Now we will start the session very soon, Professor Stephen.
Okay.
Just I would like to introduce to the participants. First of all, let me take this opportunity to say a big thanks to Professor Stephen, who had joined from the Czech Republic, Ostrava University, and Ostrava Technical University. And we are very much thankful to his time and efforts, what he has kept in here. I would like to introduce first our eminent expert, Professor Stephen. Professor Stephen was born on May 16, 1977 in Vilovok, Czech Republic. He studied electrical engineering at VSB, Technical University of Ostrava, where he earned an MSc degree in Control and Measurement Engineering in 2000 and a PhD degree in Technical Cybernetics in 2004. In 2015, he habilitated in Technical Cybernetics and has since been working as an associate professor at the Department of Cybernetics and Biomedical Engineering Faculty of Electrical Engineering and Computer Science at VSB Technical University of Ostrava, Czech Republic. At present, he delivers lectures on cybernetics and control systems. His primary area of expertise include modeling and simulation of dynamic systems, control theory, automation, and the design, implementation, and deployment of control algorithms using soft PLC system. As a researcher, he has contributed extensively to his field according to the Web of Science. That means Web of Science, he has authored even more than 106 documents with an H index of 10. Similarly, in Scopus, he has authored or co-authored 108 documents and an index of 12, H index of 12. This reflects his impactful contribution to the academic community, and we are fortunate enough to have he is joining us today as an expert to deliver the session to all of you. And I hope so you are going to enjoy his session. It is basically based on the control algorithms and all those things and applications, basics, everything, every aspect of the adaptive control will be going to deliver. That means just I am looking forward to his lecture. And thank you, Professor Stephen. Thank you for joining us. Now you can share your slides.
Okay. Thank you for the introduction. Now I'll try to share my screen. Okay, you should see my screen now. I'm switching slides. Can you see also the changes, the switching between the slides?
Yeah, everything is working.
Okay, nice. Everything is ready. So, welcome everybody once again. First of all, let me thank you very much, Dr. Giri. It's an honor and pleasure for me to be here with you today. First of all, I should explain the title of my presentation, Applications Beyond Microgrids. It means the control strategies I'm going to propose and to present. It's a set of algorithms which may be applied for a wide class of processes, including microgrids. Some examples I'm going to present will be more general, some focused on other fields, but the proposed methodology itself can be applied at microgrids. As suggested at the end of PID and nonlinear model predictive control sections. So obviously, like the title suggests, there will be two main areas, PID and model predictive control. I considered these two topics in terms of usefulness, applicability, and quality of control process. The character of my presentation aimed at providing integrated and comprehensive insight, giving most of preliminaries, including basing well-known facts. However, I hope there will be some new ideas. Main framework or keywords, you can say it's everything is connected somehow to optimization, H infinity specification, optimal control, predictive control, and receding horizon used for this nonlinear predictive control. I have to say that my work has been much inspired by my colleagues from University of West Bohemia in Pilsen, Faculty of Applied Sciences, who also work in NT Center, which means New Technologies for the Information Society. So we have a very long and good cooperation, 20 years almost. Okay, I think I can skip this personal introduction because I was already introduced. However, then there is some things that haven't been said. So apart from teaching, of course, I have some PhD students, and we deal much with the industrial partners having some common projects together. So there's a lot of activities. Like it was said, my professional orientation is modeling and simulation, control theory, automation, and implementation of control algorithms. Okay, after I created this presentation, I was wondering if ChatGPT might generate some nice motto. So I tried it. You can see what I got. So it's here just for fun, but I liked it, so I put it here finally. So the first one, innovation in control, is not just solving today's problems, but anticipating tomorrow's challenges. That's one I like. So it's here. Also, I'd like to thank 2 projects. So here is my acknowledgements. I have to thank the Research Center on Advanced Mechatronic Systems and the Refresh project, which is the international project that deal with excellence in research. So thanks to this, I was able to complete this presentation. Okay, like I said, I used 2 sections for my presentation, 2 parts. PID, which I will mention, it will be about simple PID loop first, then H infinity specification, then some optimization techniques, and of course examples. And similarly, as for MPC, there will be some categorization, definition, formulation of the problem, and of course examples. And finally, future works, challenges, and gaps possibly. Okay, how to start speaking of PID in concise way. I have to say that, in my opinion, it is still worth dealing with PID, because many people consider this to be an old topic that can be replaced by AI. However, combination of PI and PID is still used in about 85% of industrial applications. So it's definitely not an outdated topic, it's still in use. To warm up on PID topic, we can start with the description of a simple PID loop, mentioning some specific requirements. So the general formulation of the design problem for a simple control loop can be described by the scheme you can see on the right side. So what we require is that the output value has to follow the set point in every moment as possible, independently of the effect of disturbances. There can be some input and output disturbances, also noise of the sensor. So this is like freely formulated requirement that can be divided into 3 specific ones. First, it's quality of tracking of the set point, which is also called servo problem in literature. Then quality of disturbance rejection, which is called regulator problem. And finally, request for robustness with regard to the quality and stability of the control. If you take a look at the right side of the picture, you can see this simple control loop containing 2 blocks. Remember S and T sensitivity function, which is S is sensitivity function between output disturbance and the actual output, and also big T, which is also called closed loop transfer function, or it's just another sensitivity function. So remember this for further talks. Okay, so the requirements I just mentioned are closely related to the quality of control, which can be expressed in several ways. You probably know that we can define a few parameters related to the time domain. So it's overshoot, it's rise time, it's settling time. We have some definitions, so it's just displayed here just for comprehension. Also, the frequency domain, we can specify at least two parameters based on open loop circuit, which is stability reserve, or technical term is gain margin, or amplitude safety. It's a change of amplification which brings the system to the limit of stability. And then it's phase margin, or phase safety. So it's a negative change in the phase which brings the closed circuit to the end of stability. So yeah, we can determine these values from both open loop diagram. And finally, there are some integral criteria which we use to evaluate character of control process. Several types are used, such as integral error, integral absolute error, integrate time absolute error, or integral square error. Each of these is better or worse for a specific category of systems. However, the lower value of the cost function we have, the better functionality of the controller we have. So, there are many attempts in research papers to formulate requirements and to reflect quality of control. Like I mentioned, used time domain, frequency domain, integral criteria, or combination of all of those for the purpose of PID design. However, it also includes my own paper, which you can see on the right side upper corner. So I wrote this 9 years ago. It considers formulation using time and frequency domain. It's aimed at design of PID controller based on global optimization technique. However, I moved a little bit in recent years, so I myself iterated to more elegant solution. I propose basic idea of expressing all of the requirements that we place on control circuit by one or two parameters only, which is so-called MS. It's a maximum sensitivity, and MT. It's also maximum sensitivity, but on closed loop control circuit. It's obvious from the picture. So it's actually, from mathematical point of view, it's supremum on the S and T function. So we can define hypothetical or ideal requirements. We of course want that the sensitivity function S should be 0 for all frequencies possible, and for closed loop sensitivity function T, it's similarly, we wish to have this equal to 1. That's totally ideal. So real requirement, considering some physics and reality, is that the maximum or magnitude of S and T are below some threshold. Okay. Typical requirements on S and T are maximum sensitivity below 2, which guarantees gain margin and phase margin into some recommended values. Okay. On the right side of the picture, you can see that there is a relation between all of the parameters used to analyze the quality of control. This function, or the relation between those parameters MS and MT, it's not analytical function, so there is a relation, but we cannot really express it. But there's a relation which is important. Typical constraint that we can define on sensitivity function looks like this. As I previously mentioned, it can be maximum sensitivity, MS, but not only this. Apart from this, we can express a requirement on shape of sensitivity function, which is especially useful if we know what range of frequencies we would like to suppress. All of these can be expressed using the filter WS. which is actually the constraint. You can see the blue curve over here. So this approach actually reflects evaluation of so-called nominal performance, which is the same thing as evaluation of robustness of PID controller. By the way, the term robust PID versus robust design will be mentioned later on, because there's a small difference between those terms. Okay. Okay. Since the beginning of boom in control design, which dates back to half of the last century, all researchers have always wanted and looked for effective methods. What does that mean? Let's summarize what requirements we can formulate. So requirement for effective design method is first versatility. So it means it should be applicable to a wide range of systems. There are many methods. There are more reasons, but I try to put here the main reasons, which is difference between stable, unstable system. You can have a non-minimal phase system. You can have oscillatory. You can have static, astatic. Also, order of the system plays important role, and you can possibly have a time delay in your system. So there are many variations, which prevents the reality from having just one method. Adaptability is another important requirement, so it should have possibility to introduce specification that captures the essence of real control problems. And also, good method should give you a clear answer. It means, okay, if the controller exists, and then give it to me. And if it doesn't exist, just tell me why. That's in simple. What does that mean? Okay. We can conclude that no universal or versatile method exists. However, the proposed method using H infinity is applicable at vast majority of the system. So it's I would say, very effective method. Okay, this slide I created here, I put it here to give an overview on the general H infinity control problem. Even later on, I will only discuss the subset of such a problem, because the stuff you see at the moment is really very general. So it uses general model of feedback control system on the left side, which is supposed to be one of the most complex and descriptive universal formulation. So it's using W, Z, U, and Y. In the middle of the screen, you can see the mathematical description, where P is the real rational transfer matrix called the plant. R is the controller, and you can actually use lower linear fractional transformation to solve this problem. On the right side of the picture, you can see a so-called packed matrix, which describes the system if you use a full state description of the system. So you can use something which is called packed matrix. And then, for example, in MATLAB, you can use HINF-SYN function, which stands for H infinity synthesis. Or you can also have something which is called mixed sensitivity problem, where you actually apply different weighting functions for several signals in your control circuit. And similarly, there's MATLAB's function which is called mix-SYN, which is using the planned and free, or 1, 2, or 3 filters. So that are basic possibilities that you have in MATLAB. Generally, you can try to solve optimal H infinity problem, which actually means minimization of some norm. In my presentation, I'm using H infinity norm between Z and W, or between W and Z actually. So you try to minimize this. So this is optimal H infinity. However, this is very difficult to solve. And mostly in practice, we try to solve suboptimal H infinity problem, which is actually also minimization, but it's less strict than the previous one, because we just want to have this infinity norm below some threshold gamma. So it's very okay. So this optimal and suboptimal infinity problem is really wide topic. So I put it here just for comprehension. And now, okay, now I will divert a little bit from this, saying that there exists no generally accepted design method for PID controller or low order controller. The problem is that we have to respect the need for simple controller, because the practice indicates this need. Okay, we have several possibilities. What you can do is you can do the model reduction to get low order plant from high order plant, and then you can design low order controller using LQ or H infinity or whatever. Or you can go the other way. You can use LQ, R, LQG, H infinity, but as a result of this, you will actually design high order controller, which we don't want, and we have to do the controller reduction. But, however, what is most challenging is the direct design, indicated by the red arrow. So it is part of the proposed method I am going to present. Okay, let's suppose PI controller design problem first. This slide represents basic formulation to be used together with H infinity specification. So you can see the PI controller inside. You can see that the most important sensitivity functions here. It doesn't have to be only S and T, like I mentioned, but it can be also S, C, SP, which are different transfer function between various signals. So the proposed technique becomes more general. For PI controller, you can draw H infinity region in 2 dimensions. So you can actually draw Ki and Kp, which you can find the H infinity region, where inside these region, all of the controllers are valid. All of the controllers follow your requirements. Then, for example, what is typical, you can choose from all of those controllers. You can choose the best one, for example, using some integral criteria. In my proposed technique, you can easily do extension to PID. Okay, so it can use more tuning parameters. I will also mention this later on. Now let's give a simple explanation of optimization-based tuning. So we know that an integral criteria are used to compare the quality of 2 or more feedback control. That's why they have been designed. This is the first key feature. But they can also be used to design controllers if you just reverse the idea. Okay, so we actually want the control circuit to be optimal in terms of chosen criterion. The controller design then consists of finding a combination of adjustable controller parameters, for which the selected criterion will bring the smallest possible value. So yeah, you can simply write it in mathematical way. What's usually happening inside, some signals are being evaluated. Typically, it's a control error, and there's something called optimization strategy, which actually changes the controller's parameters in many iterations. What is really important here is to adding constraints. Constraints that reflect the requirement on control circuit must be added, because otherwise you can easily get to troubles. You can get trivial solution. You can get infinite values. It can lead to meaningless controllers with no functionality at all. So it has to be there. Okay, optimization job, which I will use in my technique, is used to solve the problem of designing controller. We formulate it as, or we call it, a nonlinear programming problem. It's a formulation of optimization problems in which the objective function or constraints are prescribed by nonlinear functions, which is our case actually. And the constraint may be in the form of equalities or inequalities. Written in mathematical way, it's as follows. So we minimize function of x vector, which is subject to linear inequalities, linear equalities, then so-called simple bounds here, then nonlinear inequalities, and finally, last but not least, nonlinear equalities. Sometimes in certain cases, some of the constraint may be absent, or in other situations it may be linear. If the objective function is quadratic, we speak of quadratic programming, but mostly it's very general, that the cost function is very general, it may be non-convex, and so on. Solution to such nonlinear programming, we usually use optimizers. Optimizer can be local or global. It's usually implemented for PC, or even for some embedded targets or any digital piece of hardware, almost any. Okay, so to highlight the features of the proposed solution, it's important to distinguish between local and global optimizers. So we can do this in several respects. I try to highlight in bold font what is really important. So first of all, local optimizer can converge to a local optimum, which is of course not necessarily the global best. And we want global minima. Global optimizer, on the other way, they can avoid getting trapped in local optima, which is extremely important. As for convergence, of course, local optimizers have a faster convergence. However, what is really unpleasant bottleneck, they rely heavily on initial conditions. So if you use a different initial guess, it may lead to completely different result. However, global optimizers, they are less dependent. They actually don't need any initial guess. However, they suffer from slower convergence. Also, local optimizers typically have lower computational cost. They are suitable for problems where the search space is relatively simple or smooth. With the global optimizers, we can face higher computational cost due to extensive search efforts. As for robustness, local optimizers may fail on non-convex or discontinuous functions, which unfortunately happen a lot in industrial practice. So we fight with non-convexity, discontinuous, noisy objective functions. So yeah, then it's time to use a global optimizers because they are more robust. Also, the global optimizers are better suited for high-dimensional multimodal optimization problems. Okay, what else is very important? It's guarantee of optimality. Local optimizers actually do not guarantee the global optimum unless the problem is convex. The global optimizers tend to provide better guarantees for finding a global optimum, but it's still not guaranteed. So using a global optimizer, it's, you know, you pay some cost for this. It means it's never guaranteed, but it's easy to use, and mostly it gives you very good result, even if the cost function is like non-convex, discontinued, and so on. So, okay, finally you can see some summarizing table here that puts the pieces of the puzzle together from what I have said. Okay. Nobody wants a poor optimizer. We all want good one. We prefer the best as possible. So there is incredible number of existing optimizers. To choose one, we can apply some general benchmarking. They usually evaluate the optimizers in terms of reliability, convergence, speed, ability to avoid trapping in local minimum, and so on. For example, on the right upper corner, you can see something which is called egg holder function. You can see many local minimas, local maximas, and the values actually are very close. So this is very nice, a very nice benchmark. However, it's still sort of general benchmark. So in my work, in my previous work, I tested a lot of optimizers. All of them passed such general benchmark. However, I recently devoted myself to very difficult optimization jobs. So I had to use my customized benchmark, which was identification of triple and quadruple inverted pendulums, which is extremely hard job. So it's depicted on the picture on the right side. You can see the triple and quadruple pendulum. If just imagine you can let it swing down for 1 or 2 seconds. You measure the angles, and you can tune for a triple pendulum. I think it's 11 parameters that you have to tune to match the outputs from the mathematical model and measure the data. Okay. Due to this extreme benchmarking, a set of only 3 candidates considered for further work. I tested 40. So these 3 candidates were D-Optim, stochastic fractal search, and growth optimizer. However, there were other requirements. It's mainly ability of constraint optimization. Most of global optimizers consider 3 extremes only. So we would have to incorporate some our own mechanisms to handle constraints, such as quadratic laws or augmenting Lagrangian. It will be too much of work, and there have to be some like more advanced algorithm. It's not that easy. It's better to find a good solver. Also, there's a question of implementation portability. So I actually used the original MATLAB version, and I ported into Julia. So considering above mentioned requirements, there's only one winner, which is D-Optim. You can see the reference here. It's fully available for you. It's MATLAB-based implementation of differential evolution algorithms designed for a global optimization task, which accommodates both constraints in the form of nonlinear constraint function. Okay, apart from designing PID controllers, which appear in the title of my presentation, we can provide generalization of the proposed solution for a broader cast of controllers. So it doesn't have to be PID only. Namely, we can have something which is called a fine structures controller with more parameters, or lead-like controllers with also with multiple parameters and more general formulation of the design problem. All of these have much closer to microgrids applications. Although I'm not expert in microgrids, but I know about it, that these types can be used there. I will actually try to show a few examples on this. There was an inspiration, there is an original reference dealing with the control design of two neighbor parameters only. By the way, it's written by my fellow colleagues from the University of Pilsen in Bohemia. So that was kind inspiration for me. So speaking of affine structured controller, so-called the affine structured controller can be described by a linear dependence using arbitrary proper rational tensor function, which is depicted on the right side of my slide. Typical examples, you can have a PI controller, PD, or PR controller, which stands for proportional resonant controller, which is also applicable in microgrids. So yeah, you can create something like this, even more of these structures. Or what you can also do, you can increase the control performance of your controller by in iterations, by increasing the order of existing controllers. So it's actually like adding more and more controllers to some structures. Okay, now let's declare a basic formulation of affine structures control design problem. So you can see it's similar to slide 15, which was already here. It was similar, but instead of like a affine structure controller, it depicted PI or PID controller. So now you can use affine controller. The rest of the ideas are the same. So you basically use sum of sensitivity function, one or more, by which you define your specification, your requirements. So it can be S, T, SC, SCP, and you try to minimize supremum of object H. Okay, you can use H infinity, finding H infinity region, but however, in my proposed technique, I use optimization only. So finally, I actually choose the controller, the best controller, using some integral criteria, and I place requirements by this sensitivity function or the rest of those transfer functions here in this scheme. I can do this for a servo problem, and I can also do it for a regulator problem. It's more or less general. Okay, like I mentioned, the lead-like controller. Lead-like controller are useful for improving the transient and steady-state performance of the system by providing phase compensation and gain adjustments to achieve desired stability and dynamic response. It's also used in microgrids, and you can also do the serial connection. So finally, you can have many parameters that have to be tuned like parallelly at the same time, which is a really difficult task. Okay, for the proposed solution in this presentation, more general formulation of the design problem can be used. So this slide simply declares in the mathematical way that a few things. First of all, we can use larger model set. It doesn't have to be one system only. So you can have a set of transfer functions, and if you formulate some requirements, they have to be followed for all of them. So sometimes it's called a family of process, a set or a family. Okay. Of course, you can have a different structure of your controller from PI to proportional resonant or lead lag or whatever else. Like we already said, you can use more sensitivity transfer functions. You can use different integral criteria, different weightings. So yeah, it's very general, and you can express your requirements using different filters. This slide basically brings the summary of previous slide using block scheme. So it repeats the control structure. It repeats the specifications, and it also gives a clear view of requirements for two basic types of problem, which is set point tracking or servo problem, or a low disturbance regulator problem. Okay. Well, okay, now let's make clear two terms I use too much in this presentation, which is robustness of PID controller and robust PID design. So let's declare that all PID controllers are robust up to some level. It means we usually design a PI or PID controller for a so-called nominal system, and if the actual system changes a little bit, it may still work up to some level. So this means that PID control is robust. However, the term robust design means that the robustness is considered and incorporated into the design from the beginning. So we will refer to a robust controller as one that can regulate not only the system itself, I mean the original or the nominal system, but a set of or so-called family of so-called perturbated systems. We suppose uncertainty. No mathematical model is exact, so modeling real systems consist in the art of knowing what we can neglect, what we cannot neglect, and we express the difference between the model and the real system using the uncertainty of the model. You probably know that we distinguish between structural and non-structural uncertainties. The difference is structural uncertainty or parametric means that a set of perturbated model is created by parametrization with a finite number of scalar parameters. And while non-structural uncertainty usually means frequency-dependent uncertainties, typically it can be unmodeled dynamics. So we are looking for one controller that meets all of those requirements for the entire set of processes. And robust controller design generally uses optimization in the frequency domain, usually H2 or H infinity. Okay, so I already mentioned nominal quality of control and robustness expressed by uncertainties. Now let's put together those pieces to define the robust control. Robust control is actually a connection of nominal quality of control and robust stabilization. So I'm putting this slide here because I'm actually able to solve such kind of problems with my technique. I will show you at least one particular example on this. The task of robust control is a separate discipline. We solve the task of robust control design in a much more complex way here. The result may not be a PID controller, but maybe in general form. Like I said, it also introduces two important concepts. It's nominal control quality, which is actually reflected by requirements which are placed on the sensitivity function S using a filter. And robust stability means that the controller must stabilize not only the nominal system but also the perturbated systems which suffer from uncertainties. Usually we can express or we can use filter WM, let's say, which can specify multiplicative uncertainty, which is the most common case. And it's very elegant to specify uncertainty using multiplicative way, using this filter WM. Okay, I also already mentioned an inspiration for developing my solution by the guys from Technical University in Bohemia, Pilsen. So there exists a tool called PID H Infinity Designer. I could spend a lot of time talking about it, but however, we don't have so much time, so I only use a screenshot here, so you can basically see what's happening here. What it basically does, you can define a transfer function of your process or more transfer function. You can specify H infinity limitation. You can of course select the controller type. You can use what integral criteria you want to use, and a lot of other things. Basically, it finds H infinity region. It gives nice results. However, using it for more than 2 parameters, it's a little bit tricky. You have to do it in iterations. So it was, like I said, mainly inspiration for my work. And analyzing this, I was able to find a more complex way based on optimization. What the guys use here, it's analytical way. It's analytical way of how to compute H infinity regions. So it's totally different from my approach. However, for some cases, of course, it gives very similar solution. Yeah, I will also show one example on comparison of the results from this PID designer and my solution. Well, now it's almost time for some examples, but before doing so, before proceeding to that, let's briefly declare what the examples have in common and what we need to define. So first of all, we need a cost function. It's usually some integral criteria, but it can be highly customized. Another thing that you need for optimization job is constraints. So you have to define constraints. It can be expressed by 1 or 2 filters. You can, in easier cases, you can only suppose some threshold gamma. So yeah, this is how things work with the H infinity specifications. And finally, you have to follow this inequality, which is probably very well known to you guys. So this is something which can be solved by my proposed technique. Below you can see example of typical implementation in MATLAB. It basically consists of 3 parts. Something like main script, where you easily define dimension of problem. You need to specify search space. Search space is given by lower bound and upper bound. It's not initial guess, it's just a lower and upper limit of your search space. And then you easily call the solver using this lower and upper bounds, objective function, possibly constraints, some tolerance, and some other stuff. 2 more scripts or function that you need to create is a constraint function, which usually consists of reading the actual values from the decision vector, constructing controller, evaluation of what you need. For example, H infinity norm of sensitivity function, and it's expressed in the form of a constraint value of the constraint, which has to be driven to 0 by this algorithm. And the last thing you need is objective function. So again, it's something that is used for evaluation of objective function. In our case, here we can see example of evaluating integral error only. So it's linear. So the last line you see here, it's evaluation of objective function. So yeah, the solver constantly calls these functions in many iterations, trying to reach the global solution. Okay, so here is the first typical example. As a first example at all, I choose like general problem. It's a PI and PID controller, which is based on Hfinity specification. It's for a third order system, and I have different specifications here. If I know the filter function, which helps me to formulate requirements on shape of sensitivity function, this is the case. So WS is the filter I can use with a certain threshold gamma, or I can easily, if I don't have any specific requirements on the shape of sensitivity function, I can easily use former value WS is 1, and I can only set up the threshold gamma. For example, 1.6, it can be lower. It's totally up to you as an expert. So yeah, here are the results. Like I said, it's easy to move between PI and PID or any other structures. So yeah, this is the summarizing table. So it's more or less just for you to know that what kind of problems we can solve in this. So this is not actually a robust design. Okay, it's just a regular PI and PID controller, but it's based on Hfinity specifications. You don't see any robustness, right? You don't see any uncertainty, or you don't see any set of models. Okay, now we have example. Another example. The proposed technique, like I said, can be used for robust design. So in this case, you see there is a kind of robustness here. Robustness is considered here in the form of following requirements for more processes. In this case, there are 2 processes. So you can see P1 and P2, and you are placing your requirements here, and you want to assure that all of your requirements are followed for both processes, P1 and P2. You can see the final results here on the right side of the picture. So you can see step responses, you can see both diagrams of sensitivity function S. And you can easily see for the very first look at the picture that the requirements are satisfied. So yeah, so this was example number 2, considering a sort of robustness, because robustness doesn't only mean that you need to specify uncertainty. There are more ways how to express like the robustness itself. So yeah, by other things, it can be expressed by a set of models, family, if you want. Okay, now we have example which is possibly closer to microgrids. It's a grid-connected photovoltaic inverter. I took it from some paper. So that the guys were trying to design this grid-connected a controller, which takes form of PR, proportional resonant. So the design focus here was tracking a current 50 Hz sinusoidal reference waveform. So it's basically a servo problem. Okay, so here is the formulation of the design problem. You can construct the sensitivity function. You can have your own design criterion, which is maximization of KR. So okay, here in this slide I have a comparison, because this example was also processed by H-Infinity Designer. Therefore, we can compare the results. On the right side of my slide, you can see my results from the proposed solution. You can see that my value of KR is maximized compared to what is given as optimal result from H-Infinity Designer. So I actually got a better result. It could be possibly because of local optimization they are doing, but I'm doing a global optimization. Probably it can also be maybe because of the shape of the H-Infinity region. There can be probably more reasons, but the most important is that I got a great result here. And also I find a nice modification, or better to say extension of this previous example. There are 2 references related to this example. It's again a grid-connected photovoltaic inverter, but in this case it's done in 4 steps. The first step deals with the fundamental proportional resonant controller, whose purpose is to track current sinusoidal reference waveform. But then in step 2, we consider a general affine controller with specific transfer function, and we consider the different resonant frequency because we want to suppress the third harmonic. So it's not 50 Hz, but it's 150. And it's similar with step 3 and step 4, because now we try to suppress the 5th harmonic and even the 7th harmonic. So finally, it's 250 Hz and 350. Okay. Okay, so here you see the results from my technique. It can be compared. I didn't have enough space here to put all of those pictures here, so you can see my result here. The final controller is a summation of the controller, but they have been actually designed parallelly using my optimization technique. You can see a nice way how the harmonics are suppressed. And this result is quite similar to the reference papers. Okay, I also promised at least one example on robust design using uncertainty. So here we go. Here comes the example of designing a robust a PID controller for flexible link manipulator. There's a nice reference. I put it here just for you to know. And you can easily see that the authors formulate this problem using two filters. Filter W1 means actually reflects actually requirements on the shape of sensitivity function. So basically, it tackles the problem of nominal quality of control, and they also define the second filter, a W2, which reflects multiplicative uncertainty. Altogether, you can use this block scheme here. So yeah, I got some results here, and it can be compared with the results in the reference paper. I also, of course, verified that all of the requirements were met in my solution, so I can guarantee it's okay. Finally, here in this section, I put example here, which is also close to microgrids. It's a power system stabilizer using lead lag controller for Heffron Phillips model. You are probably familiar with this model. I don't know, but I suppose we can use a series of lead lag for this type of problems. However, it's in progress. So it's, for me, it's a future challenge. It's not done yet. It's waiting. Okay. Some conclusions for this first section. So my proposed method relies on global optimization. We can design a regular PID, or we can design robust PID considering uncertainties, or a family of processes. Future works can include a controller with many parameters, like I said, a series of lead lag, for example. Also, I'd like to try application to the general H infinity problem, which would be alternative solution to MATLAB's mixin and H infinity synthesis. I'd like to point out that cooperation, especially on microgrids application, is really welcome here in terms of writing common publications. So don't be afraid to contact me. I can fully fund Q1 papers, which is important, I think. And yeah, especially lead lags controllers for the Heffron Phillips model seems very interesting way how to cope. If you guys want some source codes for any of those examples, just let me know. It's available on demand. And okay, finally, I have here potential applications of PID controls in microgrid. So you can see that, like I said at the very beginning, I still see a potential of using PID, not only machine learning, but PID. So yeah, like you see, there's a lot of topics. I'm not going to go through all of this. You can explore later on, because I hope we will have presentation at disposal. Okay. So I think it's the highest time to move to the other section, which is MPC. I started exploring model predictive control approximately 10 years before, and have been using not only for education but also for industrial applications. I soon started focusing on nonlinear MPC. The entire idea is not new, but it's still modern. It's still promising concept. It's timeless in principle, yet cutting edge in its application and challenges. So, like I said, I started focusing on nonlinear MPC. Just for very quick categorization, look at the right side of this slide. We can simply distinguish between linear and nonlinear MPC. Considering linear unconstrained case, it's nothing else than LQR. For this case, we know closed form. It's analytical solution. If we consider linear constrained case, then we have to use quadratic programming, which is still quite easy and very fast still. However, pure nonlinear MPC has to be handled as a repeated solution of optimization task each period of the control loop. So we technically measured the state, we solved the optimal control problem for a future horizon, and it may be time consuming. It can have a slow solution. You can have high requirements on computational performance, and there is no guarantee of stability. Okay, for further talks, only nonlinear MPC will be considered. Okay, speaking of background for NMPC, it's similar to background of optimal control. But before we hop on this, I have to mention something else here, because soon I will be presenting some nonlinear MPC case study. So I need to mention some hardware and software tools just briefly. So I found this Rexygen environment in 2008 when I was looking for some professional solution for a process control. It is advanced and complex tool for advanced control algorithms running in simulation or in real time on some large family of targets. It's widely used around the world, not only in education, but also in time-critical industrial applications. For example, it controls a nuclear reactor. Okay, its functionality will be demonstrated later on. Basically, you can use Rexygen Studio where you develop your project. You can easily upload it very simply to some target. It's cross platform, so you don't have to take care of if you are compiling your project for Windows or Linux or whatever. So it's really elegant. And okay, it would be for a lot of other time to talk about it, so I just move here to a brief description of some background. So background for NMPC, like I said, similar. In the beginning, we assume a general continuous optimal problem, which is turned into nonlinear programming. You can do it by some discretization scheme, such as direct transcription or direct collocation. Direct transcription simply means that you discretize all of the stuff, including control input, including states. So everything is discretized. That's direct transcription. And yeah, you can formulate a nonlinear programming job. The functionality of nonlinear MPC algorithm can be expressed by the schemes you can see at the moment. It's using model-based optimizer, which technically it can be PLC, it can be Raspberry Pi, it can be Linux-based computer, it can be PC even. So it provides necessary control inputs. It looks similar, like PID, for example. However, the core of model-based optimizer is totally different, as depicted on the lower part of my slide. So you can see that the optimizer actually uses a mathematical model, predictor, to compute a future sequence of manipulated values. And using so-called receding horizon control method, you are repeating this over and over again. You try to find the future sequence of control values, and you only use one sample of this sequence to be sent to the plant, and you omit the rest. And this happens over and over again in cycles. So this is a receding horizon, as depicted on the right side of my slide here. Also, what is important, sometimes neglected in the literature, but I think it's really important, is using some adaptive mechanism, which is used in combination with nonlinear MPC. The reasons of using this are as follows. You need to keep the model updated at all times, because you are trying to control the real objects. However, MPC concept is a model-based concept, so you need a model, and we all know that model is inaccurate, and if your model differs from the reality, you can easily get into a lot of troubles. The typical trouble is a so-called plant model mismatch. It basically means, or that in case of this plant model mismatch, you would actually reach a non-zero steady state error, which is totally unacceptable. So yeah. So okay, moving horizon estimation it's also identification method. Actually, it uses the set of measured state and estimated states in the past. So it's like a time window here that you are using. So you are using for a optimization job to find optimal parameters, which being applied, they produce the same output as the output from a real system. That's basically what's happening here. And you also need some solver to solve the nonlinear and nonlinear programming. In this case, I'm using a local solver, because using global solver, it will be extremely slow. So it wouldn't be much useful in practice. Okay, one of the most frequent cases of nonlinear MPC is MPC for tracking. So you suppose state description of your system. It's of course nonlinear, and you have a given reference, and you want to meet all constraints through time, and you want to converge as close as possible to some equilibrium defined by operating point. Okay, so this can be referred to as tracking down a piecewise constant reference signal. Of course, you can use some performance index. It's usually some difference between steady state and the actual states. It's better to show this on case study. Couple tanks, it's a good example. It's a compromise and balance between complexity and efficiency of MPC algorithm. It's nonlinear. There are 3 states, and so I was able to formulate NLP problem optimization job. So I discretize everything, including control signal, including states. So, for example, because we have 3 states on one control signal, using 30 intervals, which means 31 grid points, it makes up 124 decision variables. So I put it all together, and I have one big decision vector, okay, from which I can finally, once I find the optimal solution, I can extract the optimal value back. I can find the optimal control signal, I can find the optimal state. So, okay, it's basically using a reference generation, which is computed as equilibrium of the system. It's using a cost function, which is basically sum of squares between the actual state and the reference. And you can customize it, or you can, for example, say you want your manipulated value signal should be smooth enough, so you can really customize it very much. Okay, converting this to nonlinear programming job from the principle of using the discretization scheme, it will lead to a lot of equality boundary constraints and equality different defect constraints because of using numerical method such as Runge-Kutta or others. So finally, in each iteration, the solver is called. I use sol NP solver. It's something like very similar to fmincon. If you know fmincon from MATLAB, it's similar. It has MATLAB implementation. It has Python implementation. It's gradient free, so it's very nice solver. And during this work, I use the different techniques at different phases of the work, which may be very useful, especially for complex systems. For example, if you consider like single or multiple inverted pendulums, there is no other way how to work reasonably than using these simulation. Probably know what this was software in the loop simulation or processor in the loop simulation. So sometimes it's really necessary. Sometimes it's just the benefit, but sometimes it's necessary. So this slide basically shows several scenarios using Rexygen. So with the Rexygen systems, by the way, it's very elegant and smooth to convert between transit between different techniques, such as software in the loop, processor in the loop, and finally, once you tune your algorithm, you can easily switch to control of your real system. So, okay, finally, I can present some results here, but it's better if you see the video. I was actually planning to play this video here, but it takes 6 minutes, so I will leave it up to you. But here is the link, okay? Using this link, you will see all of the capabilities of Rexygen system. You will use how the model, how the optimizer is implemented in Python. It's quite a very nice video showing a lot of details. Okay. So, okay, discussion. Main benefit of what I have just mentioned is that we can have a prototype with nonlinear MPC functionality. It can be constructed as an external unit. It's especially useful in specific case. For example, we have the case, or we have the need for upgrade the quality of control without a demand for complete replacement. It already happened to me. Okay, so they were using some old PLCs. They said, okay, we want nonlinear MPC, but we don't want to rebuild all the things. And of course, the old PLC is not capable of computation of optimization job. So we developed an external unit, which actually provided the necessary computational result for this PLC. So there was a communication line. Okay, I chose 3 tanks just to show the capabilities, but the proposed solution can be adopted to a lot of other industrial processes. Functionality was validated using real-time embedded hardware. And yeah, I think I can move. I have I have 10 more minutes, but I also have a few more nice slides here. First of all, connection of nonlinear MPC and physical modeling in Simscape, for example. Why the slide is here? Because, like I said, MPC is complete model-based design, so we need a model. You can also you can have your model based on differential equations, but in many cases that's impossible, especially when the system is very complex. So you probably know what the physical modeling is, but if not, physical modeling involves using some environment. In case of Simscape, which is a part of Simulink, actually, it's using MATLAB-based environment to create and simulate real-world systems through block diagrams that represent physical components. You can see the difference on the right side of the picture for a very, very easy system. While in pure Simulink, you have to use some, integrators, gains, and stuff like that. But using a physical modeling, Simscape, you basically drag and drop your components, which carry the physical nature with them. You can use it for power systems, electronics, fluids, multi-body, driveline, and so on. For example, in the middle of the slide, you can see how a quadruple inverted pendulum looks like in Simscape multibody. It's very easy. You just drag and drop several components, and that's it. You have your model. Then what you can do, you can export your model to FMU, which stands for a functional mockup unit. It's basically XML file, and it's good for exchanging models between totally incompatible environment. Okay. Finally, you can import FMU back, something what you are using, for example, to Rexigen, and of course, then you can do nonlinear MPC design over it. You can do the same thing in for example, Open Modelica. You can see the example here. I don't know if you are familiar with this or not, but you can see the example. It's example of wastewater treatment plant, which is extremely hard to model. So you have to either use some physical modeling or maybe neural network. But what we did, we modeled it in Open Modelica. We exported it FMU, and we deployed an MPC. So this was a PhD thesis. It helped to save a lot of money due to minimizing overshooting control process, because the manipulated value was energy to huge air blowers. We also increased the quality of output water. So that's how we dealt with this. Apart from FMU, you can also use a neural network as models, because it can be in the role of models. Okay, in very simple words, how it works. So you use measured data, for example. Okay, here I bring the smallest, simplest possible example. You can use the measured data on input and output. You can train a neural network. And you can finally turn it to recurrent network. And yeah, finally it can serve as a model. We use this approach for example, by other things. We used it for overhead crane. We used NARCS model, which stands for nonlinear autoregressive model. So we wanted to reach. We designed an MMPC, nonlinear MPC for overhead crane, minimizing the swaying of this load. Okay. So yeah, if you want some details, just contact me. Just one small remark: apart from nonlinear autoregressive neural networks, we can also use something which is called physics-informed neural networks, which I didn't explore yet. However, we were able to obtain very nice results here for this overhead crane. Last few words. The Rexigen concept and my approach supports the digital twin. So you can actually, there's a direct link between model predictive control and digital twin. It's because one of the most important purposes of digital twin is to take care of prediction of future behavior, or so-called what-if analysis and stuff like this. So it has a very close to not only model predictive control, but to predictive maintenance. Okay, it's basically means that digital twin hosts a model running in real time, but it's also capable of doing like faster simulation for the future behavior. So it's really useful. Okay, as for future works, open challenges, conclusion. So I just point out a few of them. It's developing of scalable algorithms for high-dimensional systems. That's still a challenge or a problem. Also, there's more of them. Okay, what to say is conclusion. Maybe a few things. I used to apply this in the past for heat exchangers. I used model predictive control to predict future states because technology was very sensitive to overheating. Materials were very expensive, you know. At the moment, there is one PhD topic in progress. It's optimization of the use of electrical energy in residential laboratories. It counts with the price of electricity at the stock market, photovoltaic, you know, measurement of consumption and other stuff. So the way how this is organized is we use neural networks in the role of the model, based on log-term measurements. And MPC is above, or will be above, as a supervisory control. Okay, like with the PID, there's also a bunch of topics, potential applications of model predictive control in microgrids. Again, I'm not going through all of these, so it's just a list of them. If you feel it sounds reasonable, just let me know if you want to cooperate. Okay, thank you very much for your attention. That was end of my presentation, and because I used a full screen, I'm not sure if there was some question or not. So let me know. I know we don't have much enough time, but you feel free to contact me by email if you want. Maybe we can talk about one fast question if you want. I'm not sure.
Yeah, Professor Stephen, we will take only one or two questions. Okay. Because time is also.
Sorry, I spent so much time on this. Sorry.
No, sorry, sir. You have given your valuable time to us. It's our pleasure. Someone has asked, Mr. Hardik Pandya has asked, the expert talk about the PI and PID controller in collaboration with H infinity controller. Then what would be the outcome when H infinity is collaborated with fractional order PI and PID controller?
Okay, it could be applied if you are able to compute H infinity norm. I'm not an expert on a fractional order PID, but or you can actually define some other norm, or maybe you can use some other requirement, but I didn't explore such possibilities. I only explored H infinity norms. So my answer is it would be possible. It's for this algorithm is just about finding parameters, okay, optimal value of parameters. So yes, if you can express your requirements in the form of some H infinity norm, then it would be applicable. I don't know if I answered your question or not.
Yeah, yeah,
But
wonderful.
the result will be a set of optimal parameters.
Perfect.
If you
Perfect.
can formulate the detailed question, you can send it to me by email, because I'm not sure if I gave you a relevant response. Hopefully.
Sure.
Okay.
And I hope so. Any other query, participants, you can write in chat box. Still we have 2 to 3 minutes. We can put in front of Professor Stephen. If any query, if you have any query, please, regarding to this session. Professor Stephen, most of the queries are already that means answered in your session.
Okay.
Participants are saying thanks to you for sharing about PID and all the concepts regarding robust PID. And
Thank
you have given insights about NMPC also. And you have shared your future scope and research collaborative. That means if somebody wants to work in the collaboration, you have shown
definitely.
different things. Yes. And particularly, I am also interested in some of the things we will work out in future.
Great.
And thank you for joining us. Thank you for your time.
It was a pleasure. Thank you so much.
Thank you. Okay. Thank you so much.
Have a nice
time.
You.
Thank you. Thank you very
Bye
much. Bye. Bye. Now, dear participants, I think so. Today's both sessions are over. Now we can leave. Thank you for joining, and thank you for your participation. Thank you very much.
Tomorrow's joining time can be
tomorrow joining time is 2 o'clock. I have already shared in the schedule. So 2 p.m. First session will start. Tomorrow there will be 3 sessions. First session will be taken by some that means industrial expert Dr. Urmil Parikh from Sweden. He will join us from Sweden. And then the next expert is Dr. Sanjeet Dwivedi, who will be available online from Denmark. And once again, Dr. Urmil Parikh will deliver the his second session, and overall third session from 6. That means from I think so 5 p.m. onwards up to 6:30, and after 6:30 we will proceed for the quiz around 6:45, as Professor Jatin has informed us. The quiz is planned at 6:45. So all the participants, please be connected at 2 p.m. tomorrow. And valedictory function and participants feedback is also planned for tomorrow's last session. After that means after quiz examination, we will take the open feedback here at this platform from the few participants. And then finally our some guests are also invited if they are available. That means we will conduct the valedictory function. And you will all then after valedictory function we will say goodbye to all. And I hope so you are enjoying all the sessions, and the things are going nicely. Today's session was also very informative because I connected for 3 hours continuously, and I learned so many things from the Professor Stephen lecture. And if you are interested, you can ask him directly or indirectly by email or by some other way, whatever you like. So thank you for joining, dear friends. Thank you very much. Now we can leave. Good night to all. Thank you very much. Professor PK.
Hello.
PK sir, so now we should leave, I think so.
Yes, yes, yes. We can leave, right? Good night
Yeah.
to everyone. Yeah.
Good night.
Good
Good
night,
night to
sir.
everyone.
Good night,
Good
sir.
night. Good night. Good night. Professor Jatin, you end the meeting, please.